no non-differential points on that. So the derivative would be cosine of x, and we are only looking on the interval 0 to pi, 0 to 2 pi. Okay. And the 0 then of cosine of x, in other words, where's the cosine of x equal to 0, is actually at the top and the bottom, and that is then at x equals pi halves, thinking of the unit circle, and x equals 3 pi halves. Okay. I want to point out to you, so this is the cosine. If we are looking at a sine graph, this is the sine graph now, okay? So here's 0, here's pi, here's 2 pi, here is pi halves, and here's 3 pi halves. What happens on the sine graph is, voila, a critical number, which is the 0, the derivative happens to be a maximum, and that is not a mistake. And the 3 pi halves happens to be a minimum. So the point of this is really actually quite an important concept in calculus, that without a graph, you can find maximums and minimums of the original function by finding the zeros, or the critical numbers of the function, which is the zeros of the derivative. And that's what we're going to practice doing. Okay, last example, and I know this is a long video, but you'll hopefully break it into a couple parts and have to look back for maybe some questions that you have. Basically, when you are finding absolute extrema on an interval, if the interval is closed, I'm going to give you some steps. Okay? The first step, so this is on a closed interval, is you're going to first find the critical numbers inside the interval. So we don't include the endpoints at this point because they're within the function. 2, you're going to evaluate f of each critical number I'll put in here. So if you find critical numbers, find the y value there. Then you're going to evaluate f at each endpoint. Why do we need to do this? Because we talked about how sometimes endpoints could still be the max or the min. So the possible max and mins, absolutes, are either critical numbers or the endpoints, and we need to test all of them. Alright, let's take a look at this one, and I'm going to model the 3 steps. Okay, so how do I find the critical numbers on the interval -2 to 1? I am first going to find the derivative and set it equal to 0. That's how we find critical numbers. That would be 2x plus 2. Okay, where does this equal 0? If I move this around, or you can just obviously see it, the critical number here is at x equals -1. Okay, so I think I did that right, 2x plus 2, right? Alright, so then I go through, x equals -1 is my critical number. I'm going to evaluate in the original function now what is f of -1, because it's a potential extrema. So I plug it in, I get -1 squared plus 2 times -1 minus 4. And I get 1 minus 2 minus 4. 1 minus 2 minus 4 would give me a -5. Okay. Alright, so then I have to evaluate f at each endpoint. So we're going to do f of -2 is -2 squared plus 2 times -2 minus 4. So I get 4 minus 4 minus 4. And I get a negative 4 for that. And finally, I put in 1. So I get 1 squared plus 2 times 1 minus 4. I'm going to circle these. Which is 1 plus 2 minus 4, which is a negative 1. Okay. So these are my possible absolute extrema. What's the lowest point? This one. So the absolute min is negative 5. And it occurs at the point x equals negative 1. But the minimum itself is negative 5. That's the lowest point on this curve. And the absolute maximum is on this closed interval again, is negative 1, and it occurs at 1. Okay. Now, if you would look, notice I didn't even get my graphing calculator out once. But if you were to check this on your graphing calculator, and then let's take a look at x squared plus 2x minus 4. I hope you would see that that is true. Let's do the window. Let's make it negative 2 to 1, just so we can see it. Okay, I don't think I put that in right. I did not. X squared, there we go. Okay, so if I was filling this in, here we go. There's the endpoint, there's the endpoint. This is the maximum of that closed interval because it's the highest point, and this was the minimum. But we did that all using critical numbers and the endpoints of the interval. So that is the extreme value theorem. And tomorrow or Monday, we'll talk a little bit more about some more difficult applications of that.